A histogram is a graphical representation of the distribution of numerical data. It is an estimate of the probability distribution of a continuous variable and was first introduced by Karl Pearson. To construct a histogram, the first step is to bin the range of values, that is, divide the entire range of values into a series of intervals, and then count how many values fall into each interval. The bins are usually specified as consecutive, non-overlapping intervals of a variable. The bins must be adjacent, and are usually equal sized. If the bins are of equal size, a rectangle is erected over the bin with height proportional to the frequency, the number of cases in each bin. In general, however, bins need not be of equal width. In that case, the erected rectangle has area proportional to the frequency of cases in the bin. The vertical axis is not frequency but density, the number of cases per unit of the variable on the horizontal axis. A histogram may also be normalized, displaying relative frequencies. It then shows the proportion of cases that fall into each of several categories, with the sum of the heights equaling 1. Examples of variable bin widths are displayed on Census Bureau data below. As the adjacent bins leave no gaps, the rectangles of a histogram touch each other to indicate that the original variable is continuous. Histograms give a rough sense of the density of the underlying distribution of the data, and often for density estimation, estimating the probability density function of the underlying variable. The total area of a histogram used for probability density is always normalized to 1. If the length of the intervals on the x-axis are all 1, then a histogram is identical to a relative frequency plot. A histogram can be thought of as a simplistic kernel density estimation, which uses a kernel to smooth frequencies over the bins. This yields a smoother probability density function, which will in general more accurately reflect distribution of the underlying variable. The density estimate could be plotted as an alternative to the histogram, and is usually drawn as a curve rather than a set of boxes. Another alternative is the average shifted histogram, which is fast to compute and gives a smooth curve estimate of the density without using kernels. The histogram is one of the 7 basic tools of quality control. Histograms are often confused with bar charts. A histogram is used for continuous data, where the bins represent ranges of data, and the areas of the rectangles are meaningful, while a bar chart is a plot of categorical variables and the discontinuity should be indicated by having gaps between the rectangles, from which only the length is meaningful. Often this is neglected, which may lead to a bar chart being confused for a histogram. Etymology. The etymology of the word histogram is uncertain. Sometimes it is said to be derived from the ancient Greek sigma tau omicron sigma, anything set upright, and gamma rho alpha mu mu alpha, drawing, record, writing. It is also said that Karl Pearson, who introduced the term in 1891, derived the name from historical diagram. Examples. This is a toy example. The words used to describe the patterns in a histogram are symmetric, skewed left or right, unimodal, bimodal, or multimodal. Symmetric, unimodal, skewed right, skewed left, bimodal, multimodal, symmetric. It is a good idea to plot the data using several different bin widths to learn more about it. Here is an example on tips given in a restaurant. Tips using a $1 bin width, skewed right, unimodal. Tips using a 10c bin width, still skewed right, multimodal with modes at $and 50c amounts, indicates rounding. Also some outliers. Here are a couple more examples. Prices of houses sold in Ames in 2009 exhibit sim right skew. Aces by players in a Grand Slam tennis tournament, faceted by gender. There are more aces in the men's game. The U.S. Census Bureau found that there were 124 million people who work outside of their homes, using their data on the time occupied by travel to work. The table below shows the absolute number of people who responded with travel times, at least 30 but less than 35 minutes, is higher than the numbers for the categories above and below it. This is likely due to people rounding their reported journey time. The problem of reporting values as somewhat arbitrarily rounded numbers is a common phenomenon when collecting data from people. This histogram shows the number of cases per unit interval as the height of each block, so that the area of each block is equal to the number of people in the survey who fall into its category. The area under the curve represents the total number of cases. This type of histogram shows absolute numbers, with Q in thousands. This histogram differs from the first only in the vertical scale. The area of each block is the fraction of the total that each category represents, and the total area of all the bars is equal to 1. The curve displayed is a simple density estimate. This version shows proportions, and is also known as a unit area histogram. In other words, a histogram represents a frequency distribution by means of rectangles whose widths represent class intervals and whose areas are proportional to the corresponding frequencies. The height of each is the average frequency density for the interval. The intervals are placed together in order to show that the data represented by the histogram, while exclusive, is also contiguous. Mathematical definition. In a more general mathematical sense, a histogram is a function μ that counts the number of observations that fall into each of the disjoint categories, whereas the graph of a histogram is merely one way to represent a histogram. Thus, if we let n be the total number of observations and k be the total number of bins, the histogram μ meets the following conditions. Cumulative histogram. A cumulative histogram is a mapping that counts the cumulative number of observations in all of the bins up to the specified bin. That is, the cumulative histogram μ of a histogram Mj is defined as number of bins and width. There is no best number of bins, and different bin sizes can reveal different features of the data. Grouping data is at least as old as Grant's work in the 17th century, but no systematic guidelines were given until Sturgess' work in 1926. Using wider bins where the density is low reduces noise due to sampling randomness. Using narrower bins where the density is high gives greater precision to the density estimation. Thus, varying the bin width within a histogram can be beneficial. Nonetheless, equal width bins are widely used. Some theoreticians have attempted to determine an optimal number of bins, but these methods generally make strong assumptions about the shape of the distribution. Depending on the actual data distribution and the goals of the analysis, different bin widths may be appropriate. So experimentation is usually needed to determine an appropriate width. There are, however, various useful guidelines and rules of thumb. The number of bins k can be assigned directly or can be calculated from a suggested bin width h's. The braces indicate the ceiling function. Square root choice, which takes the square root of the number of data points in the sample. Sturgess formula. Sturgess formula is derived from a binomial distribution and implicitly assumes an approximately normal distribution. It implicitly bases the bin sizes on the range of the data and can perform poorly if n less than 30. Because the number of bins will be small, less than 7, and unlikely to show trends in the data well. It may also perform poorly if the data are not normally distributed. Rice rule. The Rice rule is presented as a simple alternative to Sturgess rule. Doan's formula. Doan's formula is a modification of Sturgess formula which attempts to improve its performance with non-normal data, whereas the estimated third moment skewness of the distribution, and Scott's normal reference rule, whereas the sample standard deviation. Scott's normal reference rule is optimal for random samples of normally distributed data, in the sense that it minimizes the integrated mean squared error of the density estimate. This approach of minimizing integrated mean squared error can be generalized beyond normal distributions. Here is the number of data points in the kth bin, and choosing the value of h that minimizes j will minimize integrated mean squared error. Freedman Diaconis choice. The Freedman Diaconis rule is which is based on the interquartile range, denoted by IQR. It replaces 3.5 sigma of Scott's rule with 2 IQR, which is less sensitive than the standard deviation to outliers in data choice based on minimization of an estimated L2 risk function where an mean unbiased variance of a histogram with bin width, and remark a good reason why the number of bins should be proportional to is the following. Suppose that the data obtained is independent realizations of a bounded probability distribution with smooth density. Then the histogram remains equally rugged, as tends to infinity. If is the width of the distribution, then the number of units in a bin is of order and the relative standard error is of order. Comparing to the next bin, the relative change of the frequency is of order provided that the derivative of the density is non-zero. These two are of the same order if is of order, so that is of order. This simple cubic root choice can also be applied to bins with non-constant width.